Okay, so on to example 2. Now, this is where we really start the factoring process. So I wanted to kind of like separate example 2 from other factoring techniques, really so we can kind of see, how factoring that we've done previously is going to relate to higher order polynomials. So in my first example, we have just a quadratic set equals 0, and we're trying to solve. We're trying to find the zeros and the multiplicity. And that's what we're going to do. If you want to be able to check your answers and kind of see how the multiplicity and the zeros compare for these different types of polynomials, just go ahead and use that link. I'm not going to refer to the graphs in this video, but I do want you to kind of use that at your discretion to kind of double check, make sure you're doing your work. But the nice thing you'll notice is I basically have the same numbers, -5, 4, and 1 for my coefficients in my polynomials. So that's going to be nice because that's going to make the work relatively easy when we're, factoring. But you can see here, I've raised them all to different powers. So in the first example, we just want to factor this as a quadratic. And basically, again, what we're doing is we're looking for two numbers that multiply to give us 4 and then add to give us -5. So we go into thinking about, all right, what are the numbers that multiply to give us 4, add to give us a -5? And since they're adding to give us a -5, we know that they both have to be negative, right? And a negative times a negative equals a positive. So immediately 2 and 2 comes to mind, but 2 plus 2 does not equal 5. So then I look at 4 and 1. But again, they have to be negative, so it's -4 and -1. So therefore, I can rewrite this. So that's -4 and -1. And then again, if you ever want to check your work, what you can do is just multiply your factors back and make sure that it gives you your original polynomial. All right, but this is the factored form. And again, I'm not going to work through the zero product property because hopefully you've seen how it works and what we can do. So therefore, we can say our zeros are x equals 4 and x equals 1. Now in this case, the multiplicity in this is just 1 because that's a linear factor, raised to the power of 1. And this also has a multiplicity of 1, okay? And that's basically all we need to do. Now again, so if you were to graph this, you would see the graph crosses and says odd multiplicity. The graph is going to cross at 4 and cross at 1. All right, so let's move to the next example. Now, we can't just factor this using the same technique that we have because this factoring technique only works for quadratics. Okay, a quadratic trinomial. It only works in this format where you want to do this, kind of cross method and the binomials. This is not the same. It's not a quadratic. This is a cubic now. So now I want to think about, all right, well, what other factoring techniques can I apply? And immediately what comes to my attention is, oh, I have a x variable in each of these terms. So why don't I factor out an x? So by factoring out an x, I'm left with x squared minus 5x plus 4. And now you can see, oh, this is the exact same quadratic that I have over there. I can easily factor that. So now 0 equals x times x minus 4 times x plus 1. Okay? And again, you could rewrite this as x minus 0 like I did previously. So you can see that this is when you use the zero product property, you could say that's basically x equals 0 with a multiplicity equal to 1. This is going to be x equals 4 with, again, a multiplicity equal to 1. And this would be an x plus 1. Oops. Let's just write that as x equal to 1. All right, that's supposed to be a -1, isn't it? I started writing this stuff too fast, and that should be x minus 1. And therefore, this is going to be an x equals 1. And again, I'm applying the zero product property, set them equal to 0, and then solve, and that equals 1. Okay, so when you have it as a cube, think about, you can't apply with the same factoring techniques that you did before. You gotta, think about factoring out common terms. You always want to factor out common terms. All right, and in this case, is really kind of the same thing, but now we see that we can even go higher. They share even more than x. They share an x squared. So again, factor it out. Look for common factors that they have. Don't be confused because you see something raised to the 4th power and it says to factor it or to solve. I'm like, I don't know how to do that. Well, yeah, we don't practice a lot with 4th power, so look into ways to simplify it to something that you're more comfortable with, which is usually going to be the case. So in this case, I can factor out an x squared, and then I'm left with an x squared minus 5. Uh-oh, I wrote that wrong. That's supposed to be a 3. Sorry about that. Wait a minute. Let's see, did I do that one right? Yeah, that's supposed to be a 3. My bad. That's a typo. So that'd be x squared minus 5x, and then plus 4. Okay? So now again, you can see that we're back to that square one. And again, you could rewrite the x squared like this. You could rewrite it as x minus 0 squared. Because if you want to write it as a linear factor so you can see where the 0 is as well as see the multiplicity, that's why writing it in that format is helpful. And then we have x minus 4 times x minus 1. Now, you don't need to write these all as linear factorization, but I think it's important, or I think it's helpful, because in this case, this is just written as the x minus 0. Right? This is written as that, as a linear factor. So here, it's raised to the second power. That means that I still have the same 0, but now it has a multiplicity of 2. So if you were to look at the graph, you'd see it bounces, whereas here it would cross, and that's all because of that multiplicity. This is x equals 4, m equals 1. Again, it's crossing. Here it's going to be x equals 1. Again, multiplicity is equal to 1. All right, so now let's get into the next example. Now, here's where it gets a little tricky, okay? Because they don't all share a common x squared, but it's to the 4th power. So how am I supposed to do something like this where I can't, it's not quadratic, right? And I can't, and it's to the 4th power, but it's multiplied, but I don't have something common. All right, so what we're going to do is it's actually going to be, we're going to relate using this understanding this factoring technique and applying it to this to the 4th power. So when we see a trinomial, we know that a trinomial can be broken into a binomial times a binomial. And if we look at this, if we were to multiply this back out, we would have x times x is x squared, all right? -4 times -1 is +4. Well, if we're going to multiply this out, okay, if we're going to factor this, we know the numbers are still kind of being the same, right? But this is a trinomial, so it can be factored into 2 binomials, right? Now, again, the last 2 terms have to give us +4, and we have a -5. So we know, we can keep these numbers the same. That hasn't changed, right? All these numbers are all the same. That's not changing. But instead of taking x times x, giving us x squared, we need to get to x to the 4th. All right. Now, you could think about, all right, well, again, how do you, what do you do when you multiply exponents? Well, remember, you add the powers. So we could do x cubed plus x, right? Or you could do x squared times x squared. So you have 2 plus 2. And that's going to be the correct one because if you remember, when you multiply, you got to combine like terms. So, you went x cubed and x wouldn't combine like. So they wouldn't combine when you'd multiply this out. So the only one that works is x squared times x squared. All right, now I'm going to multiply this out so you guys can see that this works. So x squared times x squared. I'm going to apply, the nice little FOIL. All right, let's just multiply this out. This isn't what I'm asking you to do, but I want you to verify these answers. X squared times x squared is x to the 4th. Okay, and if you did x cubed times x, you'd still get x to the 4th. But here's where you're different. X squared times 1 is -x squared. -4 times x squared is -4x squared. -4 times -1 is a +4. So if you use x cubed and x, you would have, this would be, I was writing in my head, I was thinking about that. Jeez, oh man, that's embarrassing. That's not x cubed, that's x squared. I was thinking about what to do in that mistake, right? If you had this as an x cubed times -x, you'd have -x cubed, and then this would be x, that'd be a -x, nothing would combine. But here you can see that they both have the same bases and powers, so we can combine these to give us 0 equals x to the 4th. -x squared minus 4x squared is a -5x squared plus 4. So you can see how this works. So basically, when you come up to something like this where you can't factor out a GCF and you have it as a trinomial, apply the same factoring technique you would as a quadratic, but then just raise the powers of your first terms to get to your leading power. And we'll do another one of these examples so you can see. All right, but either way, in this case, now let's go back and solve our problem. So now we have the 0 product property now in this case, I'm going to set this, I'm going to set these both equal to 0 because I'll show you 2 different ways you can do this. Okay, one way is you could, now these are not linear factors, right? So we can't say the zeros are at 4 and -1, at 4 and +1 because they're not linear. These are raised to the second power. So you could either factor these both down one more time. So if you wanted to factor them down, you could use the difference of 2 squares, Or you could just solve them using the square root method. So if I just set these equal to 0 and now solve, add 4 to both sides, I would have x squared is equal to 4, and then I'd take the square root of both sides, and x would equal plus or minus 2. And again, that's important. That's why that when you introduce the square root, that plus or minus comes. That's where it comes from. Because in this case, rather than adding 1, taking the square root, you could also just factor this using the difference of 2 squares. Because again, remember our point, when we're trying to identify multiplicity, we can't identify multiplicity when our factors are not in linear factored form. We have to make sure that our x's are linear, so then we can now identify the multiplicity. So now by applying zero product property, I would get x equals, and let's just do plus or minus 1. Now the case for all of these is the multiplicity is equal to 1. Okay, so in this example, all of my zeros, plus and minus 2 and plus or minus 1, all have a multiplicity of equal to 1. Okay, so let's go and look at this other example here. In this case, you can see, we have a factor at x. So let's factor that out. So I factor out the x. And then I'm left with an x to the 4th. And again, you might be confused, like, I've never done x to the 5th. Well, again, look for common factors. Factor out an x. And therefore, then I have, 5. It's a weird 5. 5x squared plus 4. All right? And then in this case, you might look at this and say, that's exactly what we had, right there. So I'm going to factor this, and in this case, instead of using the square root method, I'm just going to factor this out using difference of 2 squares, kind of like what I did over here. So I can rewrite this as, if I factor this, x squared minus 4 times x squared minus 1. And I'm going to write out the linear factorization, which we're going to practice here later. So if I just want to write this as a product of linear factors, right, that's what we call the linear factorization, I would need to factor x squared minus 4, which using difference of 2 squares is x minus 2, x plus 2. And I need to factor x squared minus 1 using difference of 2 squares, which is x minus 1, x plus 1. Okay. Now, unless they're asking for linear factorization, like I said, you can just stop right there. You can set each factor equal to 0 and solve, right? I mean, that's relatively easy. So you don't have to write it in this linear factorization form. But sometimes it's just, sometimes it's preferred. Now I'm going to write the solution. I'm going to write the zeros as a solution set. 0 plus or minus 2 plus or minus 1. And all of these, again, have a multiplicity of 1. So they're going to cross. So if you were to graph this, you would have 1, 2, 3, 4, 5 zeros, same as that degree, right? They're all real, and they would all cross. And sometimes you can write your zeros just out like that, or sometimes it is preferred to write them as a solution set. All right, last example. We have x to the 6. Man, how many problems have you done that have been raised to the 6th power? Probably not that many. But again, we're looking for algebraic techniques. We're looking for a pattern. We see that we can factor out the x squared. So then I'm going to factor out an x squared. And then I'm left with an x to the 4th minus 5x to the 4th plus 4. And again, you see, this is the same thing working again, right? Now, the only difference is now this is raised to a 0 power. So when I write x is equal to 0, I can say that multiplicity is 2. And then this is still going to be the same thing. So I'm not going to do the work again. X equals plus or minus 2. With the multiplicity is equal to 1, and x equals plus or minus 1 with the multiplicity equal to 1, okay? Now, again, the main important thing that I wanted to remind you is, take a look at these. Take a look at these zeros on this link. Take a look at the zeros and the multiplicity. Again, the zeros are going to be where the graph crosses the x-axis because these are all real zeros. And the multiplicity, if it's odd, is going to tell us it's going to cross. And if it's even, it's going to tell us where it bounces. So take a look at these and see how they relate to one another. Because once you've kind of get this down, I mean, this has kind of like been a summary of some graphing techniques with trinomials. As you can see in the next example, we're going to start working with different polynomials that are not just 3 terms. They're going to have 2 terms, and 4 terms. And we're going to look at different factoring techniques. So that's going to come up in example number 3.